retake of 15.2 on partial derivatives to make up for the section where the sound gave out. I don't quite remember where it was, so I'm going to take a look through this next section. We'll start from the beginning. So this we're going to be looking at what a partial derivative. This takes us back to MAT211, the calculus. So if you remember, if we have a function f of x, its derivative measures how fast the function is changing as x increases. So when we go to take a derivative of a function in general, say f of x, let's go with this as the original function, something like maybe 2x to the third minus 5x squared plus 4x minus 15. Okay. So when we go to take this derivative, if you remember, we'll primarily be using the power rule. And actually, I'll throw one more example in here. So the power rule states that to take this derivative, we take the exponent, the power, bring it down in front, multiply it by any constant that's here, and then subtract 1 from it. And we will do this for each of the terms, term by term. So we'll multiply this one by 2, subtract 1 from the exponent. 4x has actually got an exponent of 1, so we bring that in front. 1 times 4, subtract 1, we'll get 0. And if you remember that every time we have a constant, a number without a variable, its derivative is going to be 0. And that is because the rate of change of a constant, we could view this as the function y equals negative 15. That's a horizontal line which has a slope of 0. So what we get here is that the derivative is going to be 6x squared minus 10x to the first plus 4x to the 0, and x to the 0 is 1, so we won't write that. And then the 15, because it's a constant, becomes 0. So this is what it would look like. In simplest form, we would probably just write it as 6x squared minus 10x plus 4. So that would be our derivative in terms of one variable. What we do with partial derivatives is we're going to have two variables, actually a total of 3. So we've got the function value, which we could call z if we wanted to, and then we will have an x and a y variable. So we'll have 3 total variables, but we will be taking the derivative of both x and y. And what we're getting is when we have a function of 2 or more variables, we get how fast f changes as each variable increases while the others remain fixed. So we're going to look at a function in terms of 2 variables. This is building upon what we talked about in the previous lecture. And the way we do this is we take the derivative of, say, x first, leaving y as a constant, and then we'll take the derivative of y, leaving x as a constant. So we call them partial derivatives because they're really only the change of x, the slope of f, the slope of the function for each individual variable. We'll have a total of 3 variables. We'll look at what change does the, and again, one of the variables is the function itself. We could call this just as easily just the function, the variable z is the function in terms of x and y. So we'll take a look at this, and it gives us how much change in the function is contributed by each x and y in their own stead. So let's look at a few examples. How do we go about calculating the partial derivative? So we will look at one type of derivative of the function with respect to x, and that gives us how, as x changes, how the function changes with everything else being a constant. We will also do the same thing with the derivative of y. And again, when we're taking the derivative of y, we are leaving the x variable as a constant. So we have a way of writing them with this Greek letter. I believe it's a delta for change, um, but it's a small delta. I have a difficult time writing them. So you'll see me use, and the book itself will also use this from time to time. I'll just call this the derivative. So when we just had one variable, we could use this prime notation, or we could use df dx. So those were two ways of writing the derivative. What I'm going to use is this other notation, f sub x, as being the derivative with respect to x. So these two would be equal. And then I'll use f sub y as the derivative with respect to y. So yeah, using this Greek letter. Again, I think it's a delta, a little delta instead of d, kind of letting us know that this is not a one variable derivative. The way it looks, remember now that we've got three variables, we're in three dimensions. So in this case, we're holding y as a constant at some place, and then we're looking at, as x changes, how is the function itself changing. So we're looking at a tangent line at a particular point. So something that's what we're looking at when we do this. And again, this one, we'll do this throughout. So we'll find the partial derivative, and then we'll evaluate it at a given point. So that's sort of our setup. But I'm just going to do this. So let's take an example. So we've got this function, x squared plus y squared. So if we go to take the derivative of this function, the partial derivative with respect to x, we're going to take the derivative of x. So we've got x squared, 2 comes down, subtract 1 from the exponent, we get it to the first power. We're going to treat y as if it were a number. So it's, some number like 3 squared. 3 squared is 9. Take its derivative, it's going to be 0. So the partial derivative with respect to x is simply 2x. Partial derivative with respect to y, we do sort of the same thing, but this time we let x be the constant. X is just a number, maybe 2. So 2 squared is 4. You take its derivative, you get 0. Derivative of y as a variable, the 2 comes down, and you get y to the first power. So our derivative with respect to y is simply 2y. And that's a partial derivative. So we're taking derivatives with more than one zero. More than one variable. And here they're just showing that the notation I've been using is the same as theirs. You could use either one. Let me see if I can do this. I have a harder time making that Greek letter, so let's see if, it's okay. Mine, I don't like the way that looks, so this is a lot easier for me to write. Okay, so we can use either notation, but just be familiar with the book may throw this at you. It's just the derivative with respect to y, partial derivative with respect to y. Okay. And again, what is this? It is the rate of change of the function. And this first one is as x changes, x is a variable, and then you let y be a constant, a number. It's not going to change. You're only changing x. And the partial with respect to y, again, here we'll go partial with respect to x, partial derivative with respect to y. Another way to write it, it's the rate of the function that the function's changing as y changes, and we're holding x constant, fixed. So let's just look at some examples. These will be similar to the homework. And so we've got the partial with respect to x, partial with respect to y, and then we evaluate them at particular points. Here's an example. We'll first find partial derivative with respect to x. This one, 2, and so x is a variable. 2 times 3 is 6. Subtract 1 from the exponent, and we get 1. So that's the derivative here. Remember, we're taking a derivative. When we take the derivative of y is a constant because we're focusing on x as we're holding y constant as we change x. So this becomes the derivative of a constant is always 0. This term, we come and take its derivative. Derivative of x, the 1 comes down. Subtract 1 from the exponent, you get x to the 0, which is 1. So it's the derivative of just x is 1. And finally, this last one, it's a constant, already a constant. The derivative of 1 as a constant would be 0. So just to simplify this a bit, we get 6x plus 1. That's the derivative, the partial derivative with respect to x. Let's go ahead and do the partial derivative with respect to y. See how this changes a little bit. Let's change colors. So when we're taking now, emphasize we're doing a different color. Partial with respect to y. So the derivative of 3x squared, since x is now fixed, that's going to be 0. Derivative of y to the third, y is a variable now, so we bring that down. 3 comes down, we have minus 3y squared, derivative of that. X is a constant, so we bring that down. And when you take the derivative of a constant, you get 0. 1 is already a constant, it's a number, so when you take that derivative, you get 0. So the derivative with respect to y is simply negative 3y squared. Now we can also evaluate each of these at a given point. We'll go with 1, negative 1. Going to use function notation here. So we're going to plug in 1 for x, negative 1 for y. So this is our function we're working with. So 6 times 1 plus 1. Notice there is no place to put y, so we don't put it in there. That's going to give us 7. And we take the partial of y with respect to y, and we evaluate it at this point. We plug in 1 for x and negative 1 for y. And again, switch colors here. This is the function. This is the derivative we're working with. So we get negative 3, negative 1 squared. Negative 1 squared is 1 times negative 3 is still negative 3. Here's another example, and this is where we'll see that in these two examples, since each one is individually either an x or a y, and we're taking one or the other. So we take the derivative with respect to x. Notice how y just dropped out. When we took the derivative with respect to y, all the x's dropped out. But that does not always happen. So in this case, let's go with green. We're going to take the derivative with respect to x. 10,000 is a constant, so that derivative is 0. X is a variable, so x to the first comes down. We get a minus 40, x to the 0, which is 1. It's just 40. Take the derivative of 20y. That's a constant because we're holding y constant, so that is a 0. Now this 10xy, we're treating y as a constant. So what we really look at this is really, maybe think of it as 10y x. where this 10y is some number. It's a constant, right? So when we take its derivative of x is 1. The 1 comes down. And then you get x to the 0 power, which is 1. So this derivative with respect to x is minus 40 plus 10y. The derivative with respect to y, 10,000, its derivative is still 0. Derivative of negative 40x, that will be 0 because x is a constant. Derivative of 20y will be plus 20, y to the 0, which is 1. And this last part, again, we'll think of this as 10x, y, derivative of y, the 1 comes down, you'll get 10x, y to the 0, which is 1. And so the derivative with respect to y is 20 plus 10x. And then you can plug the point in for each of these. Derivative with respect to x at 1, negative 1. So that's our function right here. We're going to get negative 40 plus 10, and we're substituting in for y, which is negative 1. Negative 40 minus 10, negative 50. Take the derivative with respect to y. We're going to plug in 1, negative 1. So that's this one here. So we're going to get 20 plus 10 times 1. We're plugging in for x, right? Not y. And so we get 20 plus 10 equals 30. So what this is saying is as the function is changing in the y direction by 30 at this particular point. So if we go, so again, this is a z value, right? It's not, but it's not that the z is equal to 30, it's that it's going to change by 30. Same thing up here. When in the x direction, at this point 1, negative 1, what is happening to the z value? It is going to be decreasing by 50. How do we figure out what z is? We come back to the original function, and we plug in this point 1, negative 1. This will give us what z is at that point. So we get 10,000 minus 40 times 1. And this takes us back to the previous assignment. Plus 20 times negative 1. Plus 10 times 1 times negative 1. Let's see, that's going to give us 10,000. It's 40 minus 20. This will be negative 10. So that is, oh, these are a bunch of negatives, 60, 70. So 10,000 minus 70 is going to be 9,930. That's what z is equal to. And if we change in the y direction, here, it's going to increase by 30. So what's going to happen when we move, so the point, don't change the x, but change the y, increase the y by 1, then what's going to happen to the z? It's going to go up by 30, so it's going to be 9,960. And this in business we call the marginal, right? We increase something by 1, the marginal cost. if we increase the x coordinate by 1, so we're going to go to 2, we'll leave the y unchanged. What's going to happen is we're going to lose 50. So here was z 9930. We're going to lose 50 more. We're going to be at 9880. And again, remember this is just a sort of predictive value. It might not be exactly at this because as things change, we're changing between that. But this would give us an estimate, a linear estimate, increasing. This is a change x by 1. I don't know why we need the p there, but that's what would happen. Okay, so hopefully it's making some sense as you go through things. This last part is just to help you build understanding. This homework, you just need to be able to find the derivative with respect to x, derivative with respect to y, and then these values at these points. But in finding them, I want you to understand what you're getting. Okay, a couple more examples. A little bit more complicated. Here's one with x squared y cubed. So again, we will start off with finding the partial derivative with respect to x. So in this first term, we're going to get 2x to the first power, right? That's its derivative. The y to the third is a constant, so it tags along for the right. Nothing changed. We're taking the derivative of x, so we get x to the third. The 3 comes down. Subtract 1 from it, it's x squared. The y tags along for the ride. Just comes here. That's what that term becomes. And the final term, we take the derivative of x, that's 1. Y just comes along for the ride. 1y or just y. So that is our derivative with respect to x. Derivative with respect to y. Now, in this case, let's go ahead and change colors. Function with respect to y. So now we're going to take the y as a variable, the x as a constant. So the 3 will come down in front from the y. We'll get y squared, right? We took its derivative. X is just tagging along for the ride, so it does not change. In the next term, second term, y squared is our variable. We take its derivative, the 2 comes down. We get y to the first power, subtracting 1 from the 2. And the x to the third just tags along for the ride. The final one is we're taking the derivative of y. That's going to be 1, so the x tags along for the ride. So that is our two derivatives, two partial derivatives. And again, you can also find these partial derivatives at these points. So again, we'll do one of them. I got ahead of myself there. Partial of x at the point 1, negative 1. And again, we're taking this one here, and we're just plugging in the point 1, negative 1. When we do that, negative 1 cubed is still negative, so we're going to get a negative 2 here. Negative 1 squared is going to become positive times 1, so we get a negative 3. Negative, negative, make a positive. So negative 5 plus 1, we should end up with a negative 4. And I'll leave the 1 here for you to do as a, go ahead and work it. Let's look at this one. So this is going to be a little bit more challenging. We'll just focus on finding the derivatives. This part of plugging in the points should be a good practice from previous lesson. So here we've got a chain rule, right? We've got an inside and when you take the derivative of a function using the chain rule, we're going to get, just put, there's an inside part of the function. When we take this derivative, we get the derivative of the outside function, the inside unchanged, multiplied times the inside function, the derivative of the inside function. Okay, so how does that work? Okay, the outside function on this one, here 11, the 3 comes down, the inside does not change yet, and we subtract 1 from the exponent, so we're going to get 2. So that's the derivative of the outside. We're now going to multiply by the derivative of the inside, and when we look inside here, all we have is 2xy. Taking the derivative, we're treating x as a variable, so this the derivative of x is 1, so this is 2y plus 1. The derivative of 1 is a constant, or 1 is a constant, so its derivative is 0. If you want, you could put that there, but it's going to quickly disappear. And we can just write this such. And if you want to simplify, we could do 3 times 2, so it's going to be 6y, 2xy plus 1 squared. Taking the derivative with respect to y, we get a very similar result. The outside is exactly the same. Squared, right? Subtracting 1 from the exponent. But the inside now, we're taking the derivative with respect to y. Y is our variable, x is a constant, and so we get 2x remaining because the derivative of y is 1, and then the derivative of 1 is 0. So we get 6x, 2xy plus 1 squared. Again, you can plug in each of those points, and you'll be asked to do that in the homework. We're going to just skip over this, but you could read through it. It's basically going to introduce this concept of uh, marginal cost. And so when we take this function, the derivative with respect to x, there's only one x variable, so 10,000 is 0. Derivative of 40y is 0. So this one here is just going to be 20. The derivative with respect to y, the partial with respect to y, in 10,000, its derivative is 0. This is a constant, derivative is 0. So this partial with respect to y is simply going to be 40. These are marginal costs. And if we go back to the original question about, we would see that the Ultra Minis cost $20 to produce each. And the big stack speakers, they cost $40 to produce. So to produce one more is going to cost us 40, or if we're doing the Ultra Minis, it's going to cost us 20. That's a marginal cost. And that comes directly from the derivative. So they work it out here. Marginal costs. If we have a first derivative, just thinking back to MAT210, there's also the second derivative, and that just means we're taking the derivative of the derivative. So there's actually 4 partial derivatives. I'm not quite sure what happened to this slide, but there is, and it kind of goes first. So there's the derivative of x with respect to x. So there are 2 partials that come off of, so I guess we'll start this. There's a function, And then we're going to, from that function, we get a partial with respect to x, and we get a partial with respect to y. These are derivatives. So these are first derivatives, first partial derivatives. Okay, and then from the derivative with respect to x, we get two second derivatives. You get the partial of x with respect to x and the partial of x with respect to y. We'll go through a few examples. And then with the partial with respect to y, we also get two partials. We get the partial of y with respect to y and the partial of y with respect to x. So there's two second partial derivatives for each partial derivative. So it's, I guess they're both here. So we'll do both of these. Now they want us to calculate, they use this notation. Again, I like to use the notation for this one. This is the partial of x with respect to x. Notice x has been both times. This is the partial of y with respect to y. This is the partial of x with respect to y. This is the partial of y with respect to x. We're going to see that these last two are always going to end up being equal. They will always be. Let's just do it and you'll see. And reason why is maybe not clear, but it's a fact of life. Okay. So first off, we need the derivative with respect to x. We're going to need the derivative with respect to y. Now, these are not part of our answer because they only want the second. So the derivative we get with respect to x, we get the 4 coming down, x to the third power. We get y squared just tags along for the ride. Derivative of x is 1, so we get minus 1. So that's the partial with respect to x, the first derivative. Partial with respect to y, the first derivative is going to be, we're looking at y now as our variable. So we're going to get the 2 coming down, x to the fourth tags along for the ride, y to the first power. Derivative of x, that's just a constant, so that's 0, minus 0 if you want, but we'll just leave that clean. Now, for each of these first derivatives, there are going to be two second derivatives. So I'll do the first one. I'm going to take the first derivative with respect to x and take its second derivative with respect to x. X to the third, the 3 comes down. 3 times 4 is 12. X squared, subtracting 1 from the exponent. The y tags along for the ride. Derivative of 1 is 0 because it's a constant. Now the other second derivative we get is, again, we're working with the derivative, the first derivative with respect to x, but now we will take it with respect to y. Okay. So we're taking this first derivative and we're going to take it with respect to y. So y is now our variable. The 2 comes down. 2 times 4 is 8. X to the third, the x part doesn't change. And y squared now becomes y to the first power because we subtract 1 from the exponent. Derivative of 1 is 0, so we don't have to write anything there. So those are the two second derivatives. Taking the derivative with respect to y, we also get two second derivatives, and we're going to see that this second one here is going to be exactly identical, but this is going to be, so let's do this one first. We're going to take the derivative with respect to y, and we're going to take it this time with respect to x. Right, so this is taking this one, and when we take the derivative with respect to x, we've got x to the fourth, the 4. 4 times 2 is 8. Subtract 1 from the exponent, that's going to give us x to the third. And y is a constant, so it tags along for the ride. Notice that's exactly what we got here, that these two are equal. They will always be. And then we've got one more to do. Give myself a little bit more room here. I'll do the partial of y with respect to y. So we're looking at y as our variable. Derivative of y is just 1. So this becomes 2x to the fourth. Those all just tag along for the ride. So those are the 4 derivatives, second derivatives. Derivative of x with respect to x, derivative of x with respect to y, derivative of y with respect to x. Those two end up being the same thing. And then the derivative of y with respect to y. And then if you want to, you could evaluate all of them at 1, -1. And again, the homework, they'll have you do that, but that's just plugging in +1 for x, -1 for y, and you'll come up with a number. I do want to take a look at this last one here. I believe it's the last one, because we have to remember how to take the derivative of a function that is, I'll do e to the x squared. So e is the natural number. When we take its derivative of this function, it's its own derivative, e to the x squared. And then using the chain rule, we have to take the derivative of the exponent, which is going to be 2x. So oftentimes we would write this as 2x e to the x squared. So notice each time the derivative of an exponential has that exponential, the original exponential there. So let's kind of walk through this. So if I take the first derivative with respect to x, I'm just going to get e to the 2x plus y. I get it's its own derivative. And then I need to multiply by the derivative of the inside. The inside is 2x plus y. Derivative of 2x plus y with respect to x is just going to be 2. Derivative of y is 0 because it's a constant. Okay, so we probably will just write this 2 e to the 2x plus y. Take the derivative with respect to y, and we get something very similar. It is its own derivative, e to the 2x plus y, multiplied by the derivative of the inside. In this case, y is our variable, so the derivative of y is 1. Derivative of 2x, since it's a constant, would be 0. Again, this is just the first derivative. I guess we don't have to write that one there, right? It's really just its own derivative. That's it. And again, from each of these, we're going to get two second derivatives. Taking derivative with respect to x and taking its derivative with respect to x, we're going to get the same thing again, because that's what happens with e to the x, times the derivative of the inside. Derivative of the inside is 2x because we're taking the derivative with respect to x. Sorry, not 2x, just 2. Derivative of y is 0. And then we're going to do, let me do it down here. So that would give us 4 e to the 2x plus y. Derivative of x with respect to y, it's going to be its own derivative. And then we take the derivative of the inside, which is just going to be 1. Derivative of y is 1. Derivative of 2x is 0. So we get 2 e to the 2x plus y. From the y function, we're going to get 2 second derivatives. Derivative of y with respect to y. And we are going to get e to the 2x plus y times 1. So it's not going to change there. And then when we take this derivative with respect to x, we're going to get the same thing. And then the derivative of the inside is going to be 2, because So that's it, and then the y is 0. And notice these last two are again equal to each other. First ones are not. Okay, I think that's everything that we had scheduled, but hopefully the sound make it all the way through to the end. So I will post this and call it good.